Again, I know that we are just basically when today is the last day before the break for Thanksgiving, and that's why usually we don't have a lot of people who attend. But again, this session is going to be recorded for those who are not here today. This is the last lab in terms of actual activities that we will be doing. This is on nuclear physics. And it's quite loaded lab, actually. It has a lot of things in it. So I really want you guys, if you're not live, to really watch the entire video from the beginning to the end to understand how to do your lab, because this is this is the last lab, and it's one of actually the busiest labs that we're going to have. So I want to make sure that you guys have an understanding of this one. For those who took Physics 10 already, you must have covered this content. For those who are taking it now, most likely you did not reach this content yet. So at least my class is not, so I don't know about the rest of you. Jose, did you cover nuclear physics? Did you do radioactivity and all of these things in your class, or not yet?
No, not yet.
Yeah,
I think we're, yeah.
Yeah. Okay, so we're going to cover, I think most of the labs for Physics 11, if not all of them, they're self-contained, meaning that you really don't need to take any content before. It helps actually to have seen the stuff before in another class. But I'm hoping that the content will be basically contained. In a sense, you don't need any external resources other than this one. So it's mainly on radioactivity. There will be at the end a probability activity with the proper stuff that needs to go with it, so that you guys can do that. So let me get into the instructions quickly, if I can find it. Okay, here's this folder. Let me open the lab form. Share. Again, as I said in the intro, this is the last lab we're going to be doing in this class. 13 labs. This is the 13th week, so we were good. I guess we didn't miss any labs. I know that there were a couple of labs that needed really changes. One of them, actually only one, is the last lab that we did. I think I'm going to change the instructions so that you don't have to fill lab form, report form. What I need from you is just one paragraph, basically summary of what you did. So basically go through the laws of basically the experiment.
Did he freeze again, guys?
Sorry again. I heard, I think one of you saying that it was frozen, and it was. Sorry about that, okay? Let me check my internet to see what's causing this. Yeah, it's connected to the right internet. Okay. Can everybody hear me now?
Yeah.
Okay, so we need to go through the instructions quickly so that we don't miss much about this. Okay. So the minute I share this file now, it seems like it's doing that, at least with you guys. It doesn't do it in any other class. Maybe because of the timing. So we're going to share. Okay, that's not sharing actually. Share this file. It's still good? Okay. I can see my mouth moving on the other side. I'm going to keep that in the background. So again, the last lab you guys will do only one paragraph about it, basically stating the different experiments in it, namely the double slit, the single slit, and also the multi-slit or the diffraction grading, and their uses and purposes and so on and so forth, and what you did. And I want you to really do that on your own and basically submit it as an independent, because again, the math involved with it, when I tried to correct it and give you a different, it came up with a complete different lab report than the one we did. So I decided not to do that anymore, at least for this semester. Next semester, I'm going to fix that lab activity once and for all and make it actually in a lab form similar to everything else. So that's the only basically a problem we encountered so far. In terms of the other labs, everything I think is working fine, and it should be, everything is in the right place. Okay. So this is the last lab. As I said, hopefully you guys go through the intro first, okay, to understand that there are 4 forces in nature: the force of gravity, the force of electrostatic force, which you learned part of the electricity, and the first one part of the mechanics. Then there are the 2 nuclear forces, the strong nuclear force and the weak nuclear force. The strong nuclear force is the strongest force ever, but it has a very short range, okay? Followed by electromagnetic force, which is 100 times weaker, but that is actually can apply to any range you like, okay? Then followed by the weak nuclear force in terms of strength, that also has a short range. It does not apply to to all distances. Followed by the weakest of them all, which is the force of gravity. So these are the forces of nature. So when we're dealing with the nucleus, we don't really introduce gravity at all, because gravity is not there at all. So, okay, some words in here, that some symbols we use for this lab, okay, and actually in all of this. Z is the atomic number, and that is basically represents the chemical properties. That's the number of protons, okay? If the atom is neutral, that is also the number of electrons. So Z is the number of protons or the number of electrons in a neutral atom. So we're not going to be focused on the electrons, so we don't care about the electrons at all. So we only focus on the nucleus because we're doing nuclear physics. So Z is the number of protons, N is the number of neutrons, A is the number of both of them. That is sometimes referred to as the atomic mass, okay? So that's basically the 3 numbers that we're going to be dealing with. A itself is just Z plus N. So that's some stuff that you have to know, okay? Some words also. So an element in here, X, has A for the total number both of the protons and neutrons, and Z, which identifies its chemistry, the number of protons. Okay, so this is the element A or X in this case. Okay, and A itself is Z plus N. Okay. For example, aluminum has 27 nucleons, okay, namely protons plus neutrons, and 13 protons. So if I want to know how many neutrons it has, you subtract 27 from 13, you subtract 13 from 27, and you end up with 14 neutrons. So aluminum 2713 has 14 neutrons and 13 protons. That's in a nutshell how you come up with this number. Because the sum of the protons and neutrons is 27, therefore I can find the number of neutrons just by subtracting the 2. Okay. Xenon has 131 nucleons, basically protons and neutrons, and 54 of them are actual protons. So how many neutrons there are? 77. Just do the math, and here it's very easy. Uranium 238 has 238 protons and neutrons combined. Out of that, 92 are actually protons. So that leaves me with 146 neutrons. So this is the symbols we use in nuclear physics. Some terminology. This terminology, you use it extensively in chemistry, isotopes. And this is known, used a lot in there too, and it's used actually in nuclear physics too. Isotopes, they have the same Z, but different N's, meaning different A's too, because remember, A is the sum of Z plus N, okay? So, same Z's, basically. Same number of protons, but they have different neutrons, different masses, of course. Isotones, they have the same number of neutrons, but different Z's. They're completely different symbols, different chemical symbols, but they end up with the same number of neutrons, okay? Isobars, not to confuse it with the thermodynamics isobar, is basically the combination of protons and neutrons is the same mass basically at the end. But they have different Z's and different N's, but they could be flip-flopped, okay? Now we have the three main types of radioactivity. Because elements, sometimes they have an excess of energy, they want to get rid of it, and using the decay in this case, okay? The two forces that are involved, mainly in this case, three forces actually that are involved in this case, are the electrostatic force, because as the nucleus gets bigger and bigger and bigger, the protons from one side and the protons from the other side become too far away and they start to repel one another because they cannot attract one another from a nuclear standpoint. So there is all kinds of instability in nuclei, especially the heavy ones of them. And some of them, like uranium-238, emits an alpha particle. What an alpha particle is a helium, basically nuclide, basically a helium nucleus. Okay, there is no electrons usually involved in this case. So, what you end up with then, you lose 2 protons to form the helium. So you drop from 92 to 90, and you drop 4 nucleons. Basically, you drop 2 protons and you drop also 2 neutrons to get the number 4 in here. So you see in here 238 minus 234 is 4. Okay, so these 2 numbers, there's a conservation of this these numbers when you go from one side to the equation to the other side of the equation. This is not chemistry, by the way. When you balance this equation, you don't balance it the way that you balance stuff in chemistry, because the elements are completely different. You have uranium, you have thorium, and you have helium in here. So this is not chemistry. So this is different completely than that. This is a nuclear reaction in this case. And it's an alpha decay. The beta decay in this case, you have 2 types. You have the one that emits a regular electron, like this nuclear reaction, where carbon by itself transforms into nitrogen. So those are 2 different elements on the periodic table. Okay, and in this situation, the number of nucleons stays the same. You have 14, you have 14. But here you have 6 plus 8, and here you have 7 plus 7. So this is an isobar in this case, okay? Their masses are the same, but in this case, they are different.
So would we lose a neutron and gain a proton then?
Actually, one neutron in this case changes to become a proton and emits an electron. A proton from the 8
okay.
becomes a neutron becomes a proton, becomes positively. Remember, it was 0 charge in it initially. Okay, neutron. Now it becomes a proton, which is positive charge, and an electron, which is negative charge. So the charge is conserved. You started with 0 charge, and you end up with 0 charge at the end. Okay, so this is the electron that emerges from this decay, plus specific type of neutrino in this case that is associated with this electron. Okay, so this neutrino is associated with this one. So that's when you do the balance of the energy, you'll find that there is something missing, and that's how the neutrino was discovered, actually. Okay, which is a different particle. It has no charge. It has very little, if anything at all, in terms of mass. But that's basically the other particle. As you're sitting right now, every one of you is going. A huge amount of neutrinos are going through us because they don't interact with matter at all. Very rarely at all that they do. Okay. Now, the beta plus decay, which is another decay that involves the formation of something called a positron, which is an electron but with a positive charge. Again, sodium in this case changes into neon. Okay, both of them have the same mass. At least these 2 isotopes have the same. The isotope of this element and the isotope of the other element have the same mass together. So both of them are isobars. What happened in this case is one of the protons becomes a neutron, okay, and emits a positron, emits an electron that is positively charged. Electrons in nature, they occur only in the negative charge, in normal nature. But some of the times this positron forms, which is a positive electron. That positive electron is short-lived, because the minute it emerges from this nuclear reaction, it's going to meet an electron somewhere, bang, and it's going to disappear again, okay, and emit energy in the process. They will cancel. They will annihilate one another. If you had a chance to go to a nuclear lab, for example, I went to the one in, I didn't work in a nuclear lab because that's not one of the things I was doing, but I went to the one in Chicago, and one of the problems is trying, once you have positrons forms, how can you confine them? How can you trap them? Because it's very hard. You have to use a magnetic field super in a vacuum to really trap them, at least for a little bit of time. And then after that, they will meet sometime an electron, and then they will beg. So that's basically how they're part of what is called an antimatter. Antimatter are where the electrons are positive and where the protons are negative. So antimatter is like regular matter, except everything is backward, okay? But antimatter itself is not stable because of the fact that matter is next to it. When matter and antimatter they meet, they cancel one another and they become energy. They disappear completely. So think about it this way. Maybe there is an NTU somewhere, okay, in the universe, but if you guys meet, none of you will survive. Both of you will completely annihilate. Okay, this is one of the issues in nature that people talk about in terms of what happened to the antimatter, why there is a balance of more matter than antimatter, at least in the universe we live in. So maybe there is another universe out there that is on the other side, basically, of where we are. That is mainly antimatter, and for them, what we consider matter, which is where the protons are positive and when electrons are negative, is the odd thing, okay? But that's another discussion. Anyway, the point being in here, in a positron and an electron, when they meet, they form, they emit basically energy, which is 2 gamma in this case. A huge amount of energy will emerge out of it. So this is not stable, at least in this part of the universe. It's not stable. So in a nuclear reaction, usually this one doesn't stay too long. You see it, what is called the chamber, basically, you see the trace of it, and then it's gone because it's basically met an electron also in somewhere and then disappeared. The gamma decay, you have, for example, in here, lead is transformed into lead. Lead did not change the chemistry of it at all. So it's 8282 did not change its mass. It's 207, 207. But what happened in here, the lead itself was unstable in a sense that it had an excess amount of energy, so it rearranged itself and set correctly by emitting this gamma ray. Gamma ray, by the way, is an electromagnetic wave. It's super energetic wave. Very, very short wavelength, extremely high frequency, very high energy, but it's just light, basically, light that we can't see. You don't want to be exposed to it because of the extreme high energy. So when you see the star next to an element like this one, that is a metastable element. It's basically, it's not stable, okay? So it has a life. All of these things happen within a specific half-life, okay? Some of them take a long time to go through transition, others don't take that much time, okay, to do that. So the time in here is part of the lab experiment. Here is the first question. You're supposed to click on this link, and you're supposed to do the math. 86 minus 2 is what?
84.
So I'm supposed to go to the periodic table and find an element who has 84 protons. Okay, so I'm going to click on the table, this one in here, and allow, of course. And let me pull this one out. And let me stop sharing the screen and share with you basically this thing in here. So I'm looking for 84. This is 79. This is 80, 81, 82, 83, 84, polonium. Okay. So what goes in that insert is PO in the bottom 84. So let me stop sharing this screen in here and go back in here. So I found that it must be 84. So that's PO. So instead of writing NO, I will write PO. Let me try to write it in here. Let me get to my comments tool first. So this is what I would write in there. Oh man. Control 0. Control plus, plus, plus. So this is what I would write in here. PO 84. What should I put on the top in here? What number should I put in here?
207.
Because we do 211 minus 4, so it's 207. Does everybody agree? Okay, at least one person, a few people are on. So let's see what this 207 means in here on the periodic table again. So I'm going to go back to the periodic table. This PO, polonium, if I click on it, it gives me more information on it. So the polonium, the atomic weight is 209. I found 207. So this is not the main isotope of the polonium that I'm supposed to have. The main one is actually 209, okay? And for some reason, I ended up with 84207. So this is an isotope, okay, of this element, and there are more details in here. Let me see if I can find the isotopes in here. And it tells you what is it named after and so on and so forth. What is the isotopes? Does it give you the information on the isotopes?
Would the isotopes just mean that it's going to be like positively charged then? Since it has...
No, isotope means it's a different atomic mass. It has more or less neutrons. Like this one has 207 right? minus 84 neutrons. Right. So 207 minus 84 neutrons. 207 minus 84. So this one has 123 neutrons versus a normal polonium, which really should have 125. This one has 123. It's missing 2 neutrons. So this is not the most common isotope. Most common isotope should have 209, okay? What is this note in here? Overview. 209. So you can get a lot of details of this thing in here, including its properties. And here are the known isotopes. They range from 188 all the way to 220. What we have found is 207, this isotope. Okay? So the isotope we have found is actually the 207 polonium 84. Okay? So this has 84 protons, 123 neutrons, and gives you more of its properties. Atomic weight, it's 206.98. That tells you how strong it is in terms of is it the excess mass, how much binding energy in mega electron volts. So it's really a lot of information about this element in here. Okay, so again, let me stop sharing the screen in here. Let me go back into your questions in here. We found this question in here. Okay, this one in here. I know I have a beta minus decay. That means in this case it's this type of decay. Instead, I have a lithium in here. So the number that they have in here has gone up by 1 digit. So this one must be what in here to make this one correct? So this element has to have what?
It'd be 2, right? 2 protons.
So it should be 2, because one of the neutrons has to go back and make this one into a 3. Okay? So it's a 2. 2, but this number does not change. 8 stays the same. If you look back into this expression here, this number stays 14. So for the beta minus decay, how do we know it's a beta minus? It's this guy. Okay, the emitted and regular electron. So it's a beta minus decay. So this is a 2, and the element, if I go back into the periodic table.
Where does it get the energy to convert into a proton?
It's nuclear energy. Okay, it's an excess energy actually. It's not stable the way it is. Okay, so if I go back, which element has 2 protons? It's actually helium. So I know it's helium with a 2 in the bottom, but it has 8 nucleons. It has basically a lot of neutrons. It has 8 together. 2 of them are protons. So it has 6 neutrons. There's too many. That's why one of them will convert straight into a proton and emits an electron and becomes lithium. It moves up in the periodic table from helium to lithium. Okay? So what goes into that place in there is 2H2 8. Let me examine the isotopes of this element in here. So again, the common one is just 4. Okay? 4 nucleons, 2 protons and 2 neutrons in the nucleus, that's 4. But now I have 8 with 2 protons. That means 6 neutrons in it. That's a lot. Okay? If I examine that, here it is. This is the isotope we're talking about. Okay? So this is the isotope we're talking about. Okay? Abundance none. So it's practically nothing. It should not exist at all. Okay? Because it has a lot of energy. So it needs to get rid of it. So it's not stable. Okay? Let me stop sharing the screen. Let me go back into the screen in here. So based on the type of nuclear reaction, I can tell in here. This one, on the other hand, gives a positive electron. So this number must go down now from 9 to 8. Okay? So it moves in the opposite direction now. Okay? So the first one moves up, this one moves left, this one moves right, the first one moves right, the second one moves left. Okay? So I have fluorine in here. I go back to the periodic table by 1 digit. Remember, the 18 stays the same in this beta decays. The number of protons and neutrons as a total doesn't change. In other words, I'm dealing with isobars. Okay? So for this too. So let me stop sharing the screen and let me share with you the other screen now. I'm going to go back into the periodic table. Here is the periodic table. Here is the fluorine. Okay, so it's 9. It went back to oxygen. From 9 went down to 8. Okay, but oxygen usually has 16 nucleons. Has 16, basically 8 protons and 8 neutrons. But in this case, it actually has more because it's 18. So it has actually 18. It has 2 neutrons more than the stable version of it. So let's check again on the notes and see the isotopes. Here is the isotope we have found. Okay, this one. So this one is actually a little bit exists in nature. Okay, 0.2%. Most of the time it's the other one. Let's check the 16. The 16 is 99.796%. It's mostly the 16. The 18, on the other hand, 0.2. The 17 is even less. Okay. So these are the main isotopes. How about the 19 and the 20? This is none. The 15 is none. So these are the main ones that you find in nature. So this is a plausible reaction, actually. Okay. Let me go back into the questions. The last one to consider in here is you have gold. Okay, what is this in here? Why did I write this thing in here? This is wrong, okay? There is no such a thing in there. I think I made too many cut and paste in here. This is not there, okay? Please ignore this part, okay? For those who are watching this, make sure you follow on this part in here. Please do not include that. Okay, that's going to be the discussion point in here so that you guys don't make up a mistake. Question 1 has an error. Please fix that for the gold. Okay, so you have gold in here, 197. This is an unstable, so it's going to go into a gamma decay, similar to this one. So gold stays gold, the numbers do not change, and the gamma decay is the gamma decay. Okay?
Professor?
Yes.
Is there a way to determine which way a certain element would lean towards, like either a beta minus or a beta plus? I did notice.
When you see the minus charge in here, that is a beta minus. When you see the positive with no sign in here, that is a beta plus.
So looking at an element, like we wouldn't be able to tell if it's gonna go, if it's gonna increase
No,
its
you
neutrons or
need more
decrease?
information. You need to go back to the
Mm,
periodic table and see exactly what the calculations are. Actually, this lab is part of a huge lab that they removed it. There was some stuff in there that you could determine. You need to find where is the excess energy and how can you make it minimal, okay? Usually the calculation, not for this lab. This lab looks just for this two stuff. If you find this one, this is actually signature of a beta minus, okay? So
right.
you know the numbers do not change in the top. These numbers will go up, and you're moving up in the periodic table. If it is positive number like this one, which doesn't have a sign, that means positive. This is a beta positive in this case. So the numbers actually are going down. The top one do not change, okay?
Mm,
So that's basically how it is in this case. So this is the first question. Use a periodic table, and here that basically comment on the fact that you fixed this one and you have found all of the corresponding symbols and everything else. Okay. You might have difficulty writing the letter the word gamma in here, the symbol gamma. If you do, you just write the word gamma in this case and things like that, okay? And in here, neutrino and things like this, because you will need a neutrino, normal neutrino in here. So if you're not sure how to spell neutrino because you're probably not too familiar with it, it's written in here somewhere. Here, neutrino. Or you can write nu, because this is the letter nu actually, the Greek letter nu. It's short for neutrino. This is nu. Okay, the Greek letter nu. Okay. Again, this is the range of the nuclear reactions of the fundamental forces of nature. Gravity and electromagnetic force act on an infinite range. They have no limit where they can act, very tiny to an infinite amount. However, the nuclear forces, the strong nuclear forces, have 10 femto basically, or a femto basically meter, 10 to the negative 15 meter. The weak nuclear force is even shorter, millifemto, which is very, very tiny number, 10 to the negative 18. This, if you keep it as 1, now you compare to it everything to this one, because this is a strong force, okay, the strongest. After that comes the electromagnetic force, namely Coulomb's force, two charges pulling or repelling on one another. After that comes this one, which is the weak nuclear force, which is responsible for a lot of radioactivity, okay? And then way after this one comes the force of gravity. The force of gravity dominates the universe because of the fact that matter is neutral and everything is canceling very long distances. So at the end, it dominates, but it's very, very tiny compared to the others, okay? So that is basically to explain how radioactivity is occurring. There are other kinds of radioactivity. For example, there is this radioactivity that emits protons. Okay, and a proton has one proton and no neutrons. So it has 0 neutrons. So that's why you write it 1 and 1, which is the hydrogen atom, basically, hydrogen nucleus. Okay. So in this case, lithium, which is really not stable, will give you this kind of hydrogen, which is helium, which is kind of also not stable too, because it has only 3 neutrons in it, and versus 2, I'm sorry, it has 1 neutron and 2 protons, okay? This is very, very unstable, as a matter of fact, okay? Because now you have 2 positive charges, only 1 tiny neutron trying to glue them, so this is not stable. And then you have the hydrogen atom, which is in this case 1 proton, okay? Lithium also can transform one of the protons and make it into one of the neutrons and make it into a proton and give you in beta minus decay. Okay, so the number of nucleons does not change. Okay, again, the answer to this question is simply look at this this scenario in here. If you take 2 protons and you try to bring them closer to one another, they will repel because of this force. 2 protons are both positively charged, so if you bring them next to one another, they will repel because of the force of electromagnetic. Two positive charges, they will repel. Positive and positive do not like to be next to one another. Until the distance between them becomes this order. Okay. If the distance becomes 10 to the negative 15, at that point, the nuclear force is actually an attractive force. So it's going to overpower that force. It's going to win over this one because it's 100 times stronger. So once they reach that distance, so if they have a lot of energy, they come with tremendous kinetic energy. So they're going to repel, but they will overcome that electrostatic force until at some point they will be so close, then they will fuse. Okay? So you have two protons that have fused. But they're still not really stable, because they're still repelling each other because of that. So it's like a 1% repulsion and 99% attraction because of that. So it's still dominant. So they're still okay. Bring a third proton to the mix, now you have a problem. The same thing, you have two positive charges sitting in here, and you're trying to bring to them another positive charge, so there is more force now to overcome. So you need more kinetic energy to bring that third proton next to them. And again, if it reaches that distance of 10 to the negative 15, then that's enough for them to be stable. But the problem is the following. This proton that is sitting in here, and this proton that is sitting in here, and this proton that is sitting. These two, they're attracting one another because of this force. Okay? These two are attracting one another because of this force. But these two guys are far away. This force cannot affect them. It's this force that repels them. So they're actually, the nucleus starts to become unstable. So what you do to fix it, you bring somebody that doesn't have a charge at all, neutral. Okay, here is a neutral. This one, and another one neutral in here probably, and another neutral in here, and another neutral in here. And the more you bring, the better the situation is going to be, up to a certain extent. Because these guys do not repel at all. Those are neutrons, okay? The only thing they do is attract, actually. So they attract this one to this one. They fix this one to this one. I'm sorry. They fix this two. And now I'm getting problems with this thing in here. So they fix whatever those gaps are. So the more protons that come into play, the more stable. But if you have too many of them, then also that brings also another problem with stability in here in terms of excess of energy. So some of them start to change in here. So that is how the situation is. It's these two forces working against one another. This one is actually the one that is causing the proton not to stay, a neutron not to stay a neutron. So now you have a problem because there is an excess of protons, and the whole situation starts to come all over. The bigger the atom, if this atom becomes so many of them, okay, you have a bunch of particles in here. No matter what you do to it, doesn't matter how many protons you're going to bring in here, this, Control Z, this far away proton, and this far away proton, they cannot be fixed. They're going to repel one another because of the electromagnetic force. Because they are positive charges and they cannot be next to one another. Okay, so large atoms, large nucleides are not really stable because of this thing in here. So that is in a nutshell what's going on this level, and this is what we're trying to explore in here. Okay, again, the forces, what causes these decays. The strong force causes the decay in the alpha particle. It causes also in the proton emission, like the example for lithium. It causes also in the neutron emission, which is another kind of nuclear reaction. And spontaneous fission, for example, thorium can split itself into two different elements, element 1 and element 2. And this depends, okay? This, each time it comes up with a different configuration. So these two elements can be as simple as just basically n equals to 1, equals to 2, so where it doesn't matter, and each time is going to emit a certain number of alpha particles. So this is a big, thick, basically nucleus that is not stable, so it's going to split apart. Where it does the splitting depends on where the new elements that form are. So that is nuclear forces to you. Then you have the weak forces. The weak forces are actually the beta decay for both positive and negative. And you have also the electron capture, which looks awfully similar to the beta positive decay. So, but it captures it on the other side. In other words, when you move this one to the other side, you change its sign, and it becomes another. So you have oxygen 13, which is an isotope. Also, it captures an electron and becomes nitrogen. Okay. So in this case, the electron that is captured actually in here goes into the proton, mixes with the neutron, so that now you have so you have a proton, which is positively charged, and now you capture an electron, which is negatively charged, and both of them become now a neutron, which is zero charge. Okay, and the number is n now is promoted to the top. Okay, it doesn't change actually because you started with 8 and 5, but you end up with 7 and 6, which still. So instead of having 5 neutrons, now you have 6 neutrons. This is where the new neutron came from. The protons go down. You had 7 to begin with, and then one of them captured an electron, became a neutron. So this is actually another weak force. The gamma decay, which is just a pure electromagnetic radiation, is when the atom is not just trying to rearrange itself and get rid of the excess of the energy. So this is an example of that. So there are different ways also for the same element in here, like for example, manganese in here, in getting into different configurations. It can get into a sodium 11-30-23 by emitting a positron, or I think there is something wrong with this equation here. Okay. So when I go from 12 to 11, yeah, I think this should be a regular neutrino. I think this is an error for copy and paste. Okay, it doesn't matter. It's not going to impact any of the things that we have it in here. This occurs 91.7% of the times. That's what we'll end up with. Sometimes we don't end up with a standard sodium. We end up with a different kind of sodium, which is an unstable sodium. And sometimes actually it captures an electron and becomes sodium, which is stable, which is 0.1% of the time. Most of the time, it's the first. So again, nuclear physics is very much involved with all kinds of possibilities. This is the first, basically, kind of thing. The second thing we're going to talk about is a half-life. For an element to go from one side to the other depends on the element. Sometimes it takes this much time for half of the quantity. So if you start with 1 kilogram, for example, how long does it take for you for 500 grams to transfer and becomes the new element? So that's basically what the half-life is, half the original quantity, okay, the time it takes. Well, this depends on the element itself and depends on the excess energy and depends on the process. So this ranges from few minutes or seconds, actually, sometimes, to billions of years. Okay, like uranium-238, that it takes what, 4.5 billion years for half of what you start with to actually decay, which is as old as the entire solar system. What is the example that we were talking about? So this thing can be very, 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 very okay. So some of them take very little time, and some of them take extreme amount of time. Okay, uranium-235 though doesn't take that much time to decay. But uranium-238 takes a long time. So again, this depends even from isotope to isotope, because that depends on the energy configurations. Okay, some of the isotopes are far more stable than others. Okay, so again, so here is an example. What is it? Sodium takes 2.6 years for it to lose half of its basically substance. Okay, for the sodium decay, to decay, it takes 2.6 years. So 0 year, the beginning. Let's say, for example, you start with 1 million sample. Okay, after 2.6 years, or one half life, which is 2.6 years, a little over 2.5 years, you end up with only 500,000. Okay, or half of the quantity is gone. after 2 half-lives, which is 5.2 years, you are left with 200. I mean, 200, another 250,000 is gone. So in this case, you're left with a quarter of what you started with. In 3 half-lives, you are left, or which is 7.8 years. Out of the 250, half of it will go away. So 125,000 is gone. So in this case, you're left with an eighth and so on and so forth. Okay. So here is a question. The half-life of iodine is 60.1 days. Iodine 125, that is. How many days must one wait for half of the sample to decay? What do you guys think?
60.1 days.
60 days, 60.1.
Yeah, okay, very good. So this is not
basically said the answer.
Yes, okay, very good. So I'm glad you guys are awake, okay? Now, for the 3/4 of the sample to decay.
3/4. Oh, it's at 90.2 days? No, 90 point. 90
Something,
point,
okay? So
yeah,
you're going to
90.
add 1.5 that, okay? No, wait a minute.
It's 120, right?
Wait,
120.2.
Come
Okay.
on, Jeffrey.
Wait, 3. Wait, I'm confused. Can you? Wait,
So
3.
half of it is gone after 60 days, correct?
Yeah.
Half of the half will go also in another 60 days.
Yeah.
So 3/4 would have gone in 60 plus 60.
3/4. I thought if it was 2 half-lives, it would be 120 days, right? Which is a quarter of what it used to be, right?
Okay. Each half-life you lose half, okay? What you started with. So the first half-life, you lose 1/2, correct? The first 60 days, you lose 1/2, correct?
Yes.
How much do you have left now? After 60 days, how much do you have left?
Half, right? Half?
Half of what you start with.
Yeah.
Now, you will lose another half of what you have left, which is half, in another 60 days.
Yeah.
So you lose another quarter, basically, in another 60 days, correct?
Yeah. Oh, that's 3/4, of course.
Okay, very good.
Okay.
So how about 15/16?
Oh, jeez.
You got this one, Jeff. I don't know which one, what it would be.
So 15, 6. So that's basically, if it's a 16th, that's 4 half-lives.
Okay. So you have a fourth after 160 days. You're going to lose half of the fourth in another 60 days. In 180 days, you're going to be left with basically 1/8, correct?
Yeah.
Okay. And you lose another half of the eighth in another 60 days, which is 240 days. So in 240 days, 0.4, basically, you're going to lose the last, basically, 1/2 of the eighth, which is 1/6. So you have lost 15/16 in 240 days. Mostly is gone, basically. You're left with only 1/16. Does it make sense?
I'll be honest, not really. It gets kind of complicated when you get to like a quarter and half of a half.
Yeah, here it is.
Would it
This
be
is
240?
basically what?
Would it be like
240.4, yes.
Okay.
Okay. Almost a year after that. Well, how many 240 is what? How many? No, it's not quite a year. Still over a half a year. I mean, 180 days is 6 months. It's basically what? 8 months? 8 months? Yeah, 8 months. You still have 4 months before you lose everything. In 4 months, a little over 8 months. I'm sorry. Okay. 60 days is already a month. What? 60 days is how many? 2 months. I'm sorry. 2 months. So yeah.
2 months.
2 months, okay? I'm losing it in here, okay? So if the activity of the sample of hydrogen-3 decays to 1/8 of its original activity in 37 years, how many half-lives have passed? This is the eighth, basically.
3.
So whatever you started with, you're left with an eighth. Okay,
So it would
that
be
took
half.
37 years.
3
Sorry?
fourths. So it would be 3 half-lives, right?
3 half-lives. So 3 half-lives is 37. How much is the half-life?
A half-life would be 3. Oh, wait.
No, it's half of 37, right? So it's God,
Is it
hate
half
math.
or is it
Half-
1/3
okay,
of
so-
37?
half of.
So 1/2 of 37 or 1/3 of 37?
I think it's 1/2.
Why
What
would
time
you
is it? Is it?
Okay. Let's think about it, okay?
Oh
Let's
my.
assume.
Okay.
Okay.
Let's see.
So let's say, for example, okay, I'm not saying it is, okay? It's 12 years, okay? Let's say the half-life is 12 years.
Okay.
After 12 years, half is gone, correct?
Right.
Yeah.
After so we're left with half. After another basically 12 years, which makes it 24 years, we would have lost the other half of the half, which is another quarter. So we're left with we're left with a quarter, actually, because three quarters are gone, correct?
Yes.
Right.
Add to it another 12 years, which is about 36 years. After 36 years, we're left we're left with a quarter. So we're going to lose half of the quarter, and we'll be left with half of a quarter, which is an eighth.
Yes.
So 12
So
years.
each half-life, so it's going to be 37 divided by 3. Okay? So it's going to be slightly more than 37 years. 37 years, slightly more than 12 years, I'm sorry. Because 12 years will give you 36 after
yeah,
3 half-lives.
12.3. 12.3, yeah.
Yeah. So it's 12 years and a third of a year, which is 4 months. 12 years, 4 months.
Mm-hmm.
Correct?
Yeah.
Got it, guys?
So we could just go ahead and divide, a certain number of years, knowing the ratio or the amount that we have left of an element. We could just divide that by the amount of lives, right?
Look at this table. Look at this table in here, okay? It says after 37 years, you're left with 1/8. Here is 1/8. This is 1. This is 1/2. This is 1/4. This is 1/8. This is 1/16. This is 1/32. Okay? So now, 1/8 is here. That's all we're left with. That means we went through 3 half-lives. Correct?
Yeah.
So 37 years is 3 half-lives. So that's how we got this number of 12 and point something. Yes?
Yeah, so every step is a half-life, basically. Like, way down. Yeah. Okay. And then depending how many times we go down, we can just divide it by that number. So if it had been 1/16 of the element, we would just do 37 divided by 4, basically.
Okay. Very good. So that's how half-life works. Okay. Here is the data basically of how half-life works. Basically, it's an exponential decay. Actually, if you write the formula, there is an equation for it that is an exponential. Okay. If you have had the chance to go to a nuclear laboratory, and I visited actually another one actually in the University of Rolla in Missouri, where they have all kinds of activities, so many tables in there, and to get to the half-life is really an interesting studies in there. Okay. And then you can plot this one, the fraction with respect to numbers, and it's just straight line, okay? So it's just this dependency. So in here it's going to be an exponential, and here it's going to be just straight out line. Okay, that is how we determine the half-life. Here is what we're going to do though in our lab, okay? I'm going to explain this table in here. This is the whole lab in terms of what you guys are going to do, okay? So this is the activity. So you need to get your hands on this file, which is included part of the lab instructions, okay? You're going to download it to your computer, and you're going to start with a number 4, okay? I don't know, did I say that somewhere in the lab? We're going to start with 4, with the die of 4 faces, okay? There's 4 faces. and we're gonna roll 100 of them. If we did this lab in class, basically what I give you different decks with different basically dice in them. Each one has a certain number of faces, and the number of faces we do in the lab, actually they have, I think, like 4, 6, and all of them, okay? And that's what we're gonna be doing in here too. So we have dice with 4, 6, 8, 10, 12, and 20 faces. I don't think that we have 20 faces. I don't remember having seen that. I don't think that we even have those. So what we're going to do in here, since we have an online thing in here, we have an Excel file, we can do all of this. Okay? We can change with it. But we're going to start with number 4. All of this table in here that you're going to do in here is with number 4. So you're going to roll the dice, and then after you roll the dice, you're going to end up with a number. The die, if it's 4, it can get you either number 1 or number 2 or number 3 or number 4 up. You guys understand? So when you roll a dice, for example, most of the die that we play with at home has 6 faces, okay? So when you roll it, you either get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. What I'm saying in here is, if it comes up with 1, it went radioactive, remove it. Do you guys understand? That atom now is not part of the bunch. It's not going to go radioactive anymore because it went already. Do you guys understand this? So we have 100 dice. We're going to throw them and see which one went radioactive by looking at the faces. And if we see there is one that has showing a face 1 on top, we remove that. If it's showing any other number other than 1, we keep it. Does everybody understand how this game is played?
Yes.
So this is basically what we would have done if we were in the class. I would give you basically dice, and you would throw them, and the class will be buzzing. Everybody is doing their own and things like that, and make sure they don't fall off of the table and so on. Short of doing that, we have an Excel file that's going to do that for us. So let me open the Excel file. That's not it. So let me open it and share that with you guys. Once it comes up. So stop sharing. I'm going to share with you the Excel file. So the first thing I'm going to do in here, I'm going to make sure I have a 4 in there, and I have 100 in there. Those are the only 2 fields I can change anyway. So 100 in there. Now it's telling me 22 of them have been removed. 22 of them came with the face 1. Do you guys see that?
Yeah.
I don't need to count them, but they are coming 1. All of the others that are still in play, they are not 1. They are any number other than 1. They could be 2 or a 3 or a 4. Yes? So 22 are removed, 78 are still in place. So what I go in here doing there, so I go back into my PDF file in here. This is my experiment. Yours may be different, so please do not use mine, okay? So let me go click on this first. So I put 22 have been removed, 78 are still in play. At any point in here, the sum of these 2 numbers must be this one. You guys see that? 22 plus 78 must be 100. Yes?
Yeah.
Yep.
Okay, so I'm gonna go and start again, continue the game basically. Now, do not lose track of where you are, because if you lose track of where you are, you have to repeat the whole thing again. So now I know I'm left with 78. So I cannot say I have 100, so I need to make sure that it's 78, correct? I'm gonna put 78 now, okay? It tells me, so it removed the others, because if you were doing it in class, actually we remove them, we put them aside, okay? The ones that came up 1, we put them aside. So now we're only left with 78. Out of the 78, 58 are still in play. The other 20 are gone. So I'm going to go back into this, stop sharing, go back into the PDF file, and say I removed 20. Okay. And I'm left with 58 now. At any given point, the sum of these 2 numbers must be this one. You guys see that?
Yep.
Can anybody tell me what's the next step is in terms of this Excel file? What should I write in here? So the 4 should not change at all from now on.
N should equal 58.
And 58. It gave me 13 need to be removed, and 45 are still in play. So I'm going to go back, stop sharing the screen. Do not, if you have to repeat this lab again, do not rely on the old data. You have to start all over again, okay? That's why I'm not asking, I cannot use my data. Because if you do, you use it, you're going to get complete lot of errors. So you have to start it, make sure you're paying attention between the Excel and the PDF, the Excel and the PDF, until you complete every single cell in this table, okay? And there are 20 points in it, so 20 entries in it. So I removed 13, and at 18, 45. Okay? Does anybody understand how to go all the way to 20? You guys are supposed to complete not just up to 10, not all of this in here. This one's ignore them because they're not fillable anyways. So you cannot type anything in there. But you're supposed to go through all of this process in here using the Excel file.
Quick question.
Yes.
Is there, I'm just curious, is there a way to not get to 10 and like just have a bunch of them hit 1 early on? Just curious. Or it's just not
What do you
how,
mean 10?
like, what if a lot of them get removed from play? Is that possible?
If it is possible, that means this law that we're trying to verify is going to be a problem for us. Do you understand?
Okay. Just curious.
Okay. We're trying to say that this given atom to go radioactive is a random chance, because a given atom basically can go radioactive or not radioactive. Now, if the probability for it going very radioactive is very low, that means the half-life is very long. Okay. Versus if the probability for it is going to be very high, then then in this case the half-life is very short. That's basically what we're trying to say in here. Now, if you do the dice, okay, you increase the number of the faces, you will see that the half-life will be very long. That's why when you are looking at 4 sides to the die, this is really going to be shaky a little bit, because we're supposed to have a short half-life, but again, we probably are not going, we're going to run into a situation here, an error. But to answer your question, it should not. If it does, that's a disaster, okay? If it does, all of that. Let's say, for example, you throw all of the 100 die. If you do it at home, okay, forget about this Excel file. Take 100 dice and throw them all. What is the chance for all of them being face up 1? Do you understand what I'm saying? If you go to Vegas and collect a bunch of dice in there from Vegas, okay, and you throw all dice in Vegas, every time you throw them, you get a 7. What happened in this case? What do they do to you? What do they think they did? Do you guys understand that game where you have to get a 7, or what is it, the game that you, when you throw the table? You guys know what I'm talking about or not? In gambling?
I do. I can't think of the name.
Yeah, but the point being in here is, if it happens, I don't know who asked the question. I think it's Jeffrey. I don't remember. You're asking the question if all of them came up 1. This is the same probability for winning that game all the time and becoming a millionaire out of Vegas or whatever casino you go to. Okay, so this is the same thing. So there is no way with 100 dice, you throw them, all of them will come 1 the first time or even the second time. So there is, because for one die to show you the face 1, it's 1 out of 6 chances. Okay. Out of this, for this case, it's out of 25%, basically 1 out of 4 chances. But it's still, it's not going to happen. Okay. So you're going to continue this. So you're going to continue all the way to 20. But the numbers, you'll start running out of them basically at the end. So you're going to be in a single digits at the end. Does everybody understand how this thing is done? At least all the way to 20 cells. I want to make sure that, I know we have more than 2 people. So Alicia is on board. That's good. Okay, Samantha also is good. Okay, seems like I have everybody, since I don't have any objections. So let's continue this. So assume, do not use this data. That's the biggest warning I'm going to tell you in here. So if you do that, you're going to run into a big problem. So you're going to start honestly with your 100 data in order to get really something significant, okay? These cells do not have nothing to do with this data for right now, okay? This cell has to do with table 3. This cell has to do with table 4. This cell has to do with table 5. Okay, this cell, you're going to go through the 4 dice and you compare it and you find the error. Okay, so I'm going to show you what that is. Okay. Since this lab is a statistical experiment, one can make predictions regarding the number of dice expecting at the beginning of your 20th roll, as seen in table 3. Does your data agree? Okay, so the table 3, let's look at table 3. Table 3 says for a die of 4 faces, the chances, once you roll the 20th roll, you're going to get a number between basically 0. Okay, between negative 0.245 and 0.87. So this number should be 0. Do you guys understand? Maybe a 1 at best, because this is not going to give you negative numbers. So you're going to put the number that you get in here, basically from this experiment that you are in here, okay, that you get in there, you put it in here. And you're going to look at this, is this a 1? Because 0.87 is a 1, okay? Or is it 0? If it is either, you agree. If it is not, you don't check this number. You guys understand? So you're going to look at the number you get in here. If it is 0 or 1, you check this result. Does everybody understand this part?
We have to check it if it's 0 or 1.
If it is, basically, because that's what it's telling you. Okay?
Oh, yeah. The number
it's
range.
telling you between a negative 0 point to 0.9, basically, which is practically 1. Okay? If you get 0, and then it agrees. If not, and you're going to put the result in here, okay, from the 20th run. The one that you find in here, you're going to put it in here. And if it agrees, you say it agrees. If it does not, you say leave that alone. Don't check it. Okay? Now, you're going to repeat the same experiment instead with 6 faces. But you don't fill this table anymore. You just repeat it up to 20th time. Up to the 20th roll. Okay? You should find a number between 1 and 4. You could find a 1. You could find a 2, you could find a 3, you could find a 4. If you find a 5, it doesn't agree. 6 does not agree. Do you guys understand? You're going to do the same thing. So let's try to do it quickly with a 6, okay? 6 faces. So I'm going to stop sharing the screen. And somebody has to keep count, okay, because I will lose track of this. So we're going to start with 6 faces, and we're going to start with 100, okay? So this is run number 1. Remember, we're supposed to get up to 20. So after 1, we have 81. So somebody has to tell me, okay? This is 2. 3. Make sure I'm not making things wrong in there. This is 4. 5. 6. 7. 8. 9. 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Wow, last time I did it, I lost count. So what answer did we find after the 20th? For this experiment that I ran myself. Can anybody see what the result is?
2.
2. So I'm going to go in here, stop sharing. I'm going to go in here. Of course, you're going to do your own and put a 2. Does this check or not check? So put 2 in here.
Yes.
So it's between 1 and 4, so it's good. Okay? So you're going to do the 8. You're going to do the 10. The 4, of course, you're going to report the data in the previous table, okay? In table, what is it? Table 2, okay? So we're going to copy the data in here and check whether it checks or not. The 8, you're going to do it by yourself. So remember, pay attention, okay? Because you could easily be distracted and punch the wrong number in there, okay? You could easily be distracted and punch the wrong number, and then you have the wrong answer. So make sure you do the 8 faces. So make sure you change the phase and changes only once, because if you touch it again, it's going to randomize a number for you and mess up your last reading. So like I did in there in the Excel file, let me go back in here. So once I change this one to 8, let me put 100 in here, and I'm going to show you exactly what happened to. So 100 right now is showing me 77. If I put an 8 in here, I have a chance to change this number in here. Okay, so make sure you do it correctly. Okay, so it's telling me 87 now, so that's fine. So I'm going to put 87, and I'm going to put something else, and then now instead of putting 76 in here, I put it in here, 76. Okay. The numbers are completely a mess now. We went from 76 to 85, which doesn't make sense. So I say, oh man, I made a mistake. So I'm going to go back to 8, and the answer is 78 now, not 76. So again, I have to start to scratch here. I have to really start from 100 to make up my data is correct. 100, then 83, and so on and so forth, and continue with my reading. Okay? Does everybody understand this process in here, at least for the next table? Yes? Okay, so let's continue this. We can also make predictions regarding which roll are likely to run out of dice. So if you run out of dice on or before the 20th roll, enter it in table 4. Does your answer? Okay. This table in here, what you need to do now, when would you run out of dice, basically? Okay. It's a good idea to do both experiments in the same time. While you're doing this, you could have continued to see when you run out of dice. Remember at the end, let me go back into my simulation. Let me put back the 6 in here. And let me put back the 2 in here. Okay, so this was 20th run, okay, when I did that. So what I'm going to do now, I'm going to run it one more time. So this will be the 21st. I left with 1 dice, okay, with 1 basically die. 21, 22, 23, 24, 25, 26. After 26, I have no more remaining. All of them are gone. After 26 is done, okay? So I would come in here and put 26. After the 26th run, I ran out of basically all the material is gone. No more radioactive materials. Does this check or not check? It says if you run it 21 times up to 37 times, you will run out of dyes. And I ran it 26. Am I between that margin or not? Okay, so I need to check that, then it works in this case. And you do the same thing for the 4, by the way. You could do what I did, but it's a good idea while you're doing this, continue this until you run out of dyes. Basically, the thing with it is, it says you could run before the 20th run. Around the 13th, maybe you'll end up with nothing. Up to 23rd, okay? So you might end up with nothing before the 20th run, okay? So the table could look like this for you. It could be 0, 0, 0, 0 all the way through in here, up to the 13th, or 0, 0, 0 in here, or 0, 0 in the last 3 or so. Or maybe you still have a number like I did, but then you might end up with less at the end, okay? So this is basically for this portion in here. So let's continue the questions. You can estimate the half-life of your dice basically by saying the following. If you run the 4, for example, between 2 and 3 times, you should go to half. If you start by 100 and you run it 2 to 3 times, you should end up with nothing. And here for the 6, it says between 3 and 4 times. So this is what I'm going to do. I'm going to do the 6 again and see if indeed I will have half of the 6, which is around 50, around between 3 and 4.35. So I'm going to stop sharing the screen. I'm going to go back into my Excel file. I'm going to start with 100, and it's still the 6 faces. Okay. So after the first run, I'm not at half, am I? It's 84. So I put 84. This is the second one, and it's still not half yet, okay? 72. I have 62, and this is the third attempt, and it's still not half. 62. 53. So this is the fourth one. I'm at 53, okay? So this is almost half, okay, if you wish. So this is 4 attempts. Let's try the 5th attempt. Oops, I'm sorry, 53. 45. So it's somewhere between 4 and 5, okay? Let's go in here. For 6, it's between 4 and 5. Slightly more than 4, actually, and way less than 5, because I was at 4, around 4.5, I would say. Actually, it's a little less, around 4.3, to be honest with you, because of the, oops, not 43. 4.3. The reason why I'm saying this is the case is because, oops, I'm not sharing my screen. Yeah, it's around 4.4 and a third, because it was 53 at 4 in 45. So it was closer to 4 than 5, because 5 gave me 45. So I would say it agrees in this case, okay? And you can say the error in here, you can calculate the error if you want to. So here is in a nutshell your entire lab, okay? If it's off, you're going to come up with a big error. 4.3 is going to put it right with 0% error. If not, you're going to error it is. Just find the theoretical minus the value that you have and divide by the theoretical and multiply by 100.
Did he disconnect?
Yeah, I think it froze again.
Okay.
How's it going, Jeff? Are you understanding it?
The,
Pretty easy, right?
the algebra part, it's kind of confusing, but I'll be
Yeah.
honest. But I wasn't really paying attention to that part.
Like the half-life?
No, the half-life, I was getting it, but it was at the very beginning when at the algebra, like
yeah.
adding and subtracting was easy, but when he got to the
Yeah.
beta, I was spacing out, to be honest. I know he can hear me, but I'll ask questions. I'll ask questions, even though it's a little bit confusing.
Yeah.
But I will.
I have no idea what's going on with these things in here. Anyway, I'm hoping that you guys cannot start video. Why? Is it recording?
We could see you.
We could see you.
Yeah. For some reason, it's giving me some errors in here. I have no idea why this is happening now. It's happening only with you guys. I mean, this thing in here. Anyway, it happened actually in other classes too, somewhere before. Anyway, the point being in here is, and my internet is fine right now. I don't know. Probably my computer is going through an update or something like that. Maybe I'll restart it tonight. So this is in a nutshell your lab. There is a lot of back and forth between this Excel and this PDF file. This was part of a big lab that I used to do for my classes, and I basically put it together for you guys. So I'm hoping that you guys will not have any difficulty with it. I know somebody was mentioning, I don't know if it was Jeffrey or if it was somebody else was mentioning the fact that there is an issue with the algebra or something, because I could hear some conversation until I restart the whole program. Which part that you guys need help with?
I think for me, Jeff, yeah, I'm talking. It's just the beta, positive, negative stuff, and then going into the first link and looking at all that.
The periodic table?
Yeah, that stuff is not fun.
Just follow the examples that you have in the actual instructions, okay? And it should really make sure that the number a plus z, which is z plus n, must be conserved, and z itself also must be conserved. So if you need to add or subtract, just to make sure that it's there, okay? Now here is the deal. I'm available for you guys even during the break, so if you need help with it, please let me know. Just allow me, give me a little bit of window so that I can respond to you and make sure we're fine, we can meet. I'll be more than happy to help you with that to make sure that it moves along. I know, like I said in the beginning, we did not even cover this stuff in lecture for our class, and I know that you guys did not cover it. And for the people who took the class before, probably they did not delve into a lot of details. Did anybody remember from the previous who took this class whether or not they went into a lot of details like we're doing in the lab? No? Actually, okay. Thank you, Alicia. Okay, so actually one of the students for next semester, actually is a high school student, sent me an email today asking about to join this class for next semester, and I actually recommended more the lab than the actual in terms of content than the lecture, because we do a lot of things in the lab that we probably don't cover in the lecture as much.
Talking about physics 10, right?
Physics 10 versus physics 11, yes. Physics 10 is...
This one's way more hands-on. All that other stuff is like theoretical.
Yeah. So, and that's really the intent of it, so that you guys get your stuff to get to know things. I know in lecture, basically, we cover things, we get excited, we talk about them, and then we move on. Right now, we are in chapter, what, 26? No, which chapter we are in?
We're like on 31, 32, I think.
Yeah, 31, 32. So we're way ahead of these things in here. And I mean, not way ahead. Actually, we're behind the content than this, but we're covering so much material and still behind. Versus this one, we're focusing only on some topics, and I think I myself am enjoying it. I don't know about you guys. Okay. So I will see you guys after Thanksgiving. What we will do is I'm going to first send you further details onto Lab 11 to 12 to make sure that you guys have all of the things. I know some of you are working on the motors. Please, at least one of you guys sent me already emails in the morning about the materials and things like that. So if you need help with that, please let me know too. Others, I'm going to send them basically a report on how to do the report for the motors, because I know that they're supposed to do the second part of it. Those who are not going to do the actual demo, for the for the motor, they are going to be required to attend the final, otherwise they'll get 0 in it. And also in the next weeks, we're going to have a review for that. I'm going to also send you a link for those who want to do the motor or doing the motor to upload the video in, so that you're going to complete your assignment there, so that we can basically follow it and make sure everything is working and everything is fine.
I did have a question about the motor assignment though.
Yes.
Okay, so I did opt in to do the motor, and I put that on the lab 10
Yes.
you told us to do a few weeks ago. Okay,
Yeah.
do I have to specifically email you or about like that I'm doing it, or you're just gonna email stuff out?
No. I'm going to basically, if you're doing the motor, okay, you're supposed to be good on it. Go and get the materials that you want. You can shop around. Basically, the place I found easy to find stuff in is Amazon. Again, I don't have any ties with them, so it's fine if you can find it somewhere else. Okay, but the requirement for it, try to get a high gauge wire, meaning it's thin, at least 28. Do not get anything less than 28. Okay, do not get a thicker wire than 28. 28 would be perfect, actually. 32 also would work. Anything in this range would work. You're going to get a battery, which is a normal battery, 1.5 volt battery, which is like this one. Try to get a battery holder also with it, okay? This is a battery holder, if you can, okay? If you can't, then the other alternative is, it's going to be basically you need somebody to help you with it, is use rubber bands, okay? Like this one. I got them from Walmart, actually, the rubber bands, okay? To hold this things in place, okay? Because they need to establish contact to hold them in place on this side and also on the other side. And once you do that, try to spread the rubber. Try to be creative a little bit on how to spread the rubber bands so that they touch the nodes, okay? Let me try to make sure I do it right, okay, here. Because I placed the other solution that I have seen people use it. They do it, actually. So here is with a rubber band, okay? As you can see from this negative and from the positive. The positive, you can see it clearly, but it's touching the positive in here, okay? So now, I put my motor in there. I put the magnet on top because this batteries are supposed to be attracted to magnets. So if I put a magnet, it's going to stay on it, okay? As you can clearly see. And then this magnet is not strong enough, okay? Again, if you go to Amazon, you're going to get this magnets in there. And then make sure that you shave the ends of the wire, okay? With any kind of material to make sure, because you would want to establish contact in here. You put it in there and let it go. Okay, you have built it.
So those are basically all the stuff we need to make the motor.
I'm sorry?
Just like everything you had in your hand. Oh, okay.
Yeah.
All right.
That would be plenty. I think that would be enough. Ideally, this would be better. Okay. This is a battery holder. Okay.
Battery holder. Okay.
This is a battery holder.
Is there a way that you can... Sorry, I had a question. Is there any way that you can like put a link for the actual battery holder?
Oh, yeah, that'd be nice.
Because I tried looking for them. I did find a few on Amazon, but I wasn't too sure if that was like exactly the holder I needed.
Okay, what you're looking for is 1.5. This is a D-cell battery, okay? D-cell battery holder. Again, I'm just Googling these things, okay? And it says Walmart has it for $8.85. But that's, hold on, that's no good. Okay, wait a minute. Let me show you the picture I'm looking at. If you're gonna use this, it's not really gonna be the greatest, okay? Because I don't like that, okay? Let me go back into images to see if there is one. that would work. Let me check this one in here. I'm looking at the images, by the way, okay? No. Now, we go back in here. Okay, here is the one that I have actually. And oh man, it took me to Amazon. Did you try, guys, Amazon?
I did, but I saw some that actually had like wires on the end of the holder, and I know you
Yeah,
said you
that's,
didn't want that.
if you do that, you have to modify it, okay? You can modify it.
Yeah, I see the wires too.
Okay. This one has a pack of 4 and it should work, okay? Let me give you the link for it. I have it on Smile because I usually have a non-profit organization I help with. Okay, one of them is $649, one battery holder, and a pack of 4 is $895. I wish we were in class and we buy a bunch of them. Actually, we have them in the class. Okay, so let me put the link in here for you guys. And I'm going to show you how the, oh man, it's a million words in here. Hopefully you guys can copy that. Okay, so let me show you the how it looks like, at least on my Amazon. Where is share screen? Share. Here. Let me tell you why this is actually better than the one I have, because you have these things that have the screws in them, and you can tie around them any connection you like, okay? Including the one that I have in here. You see? In here. And you can actually adapt it to whichever you like. And these are, for this battery, these are the D-cell batteries, okay? Because this is a D battery, the one I have. If you bought a different battery, if you bought, for example, a C battery or something, you need to make sure you change the letter from a D to a cell to a C, okay? So when you're looking in here, in my search, I looked for the D-cell battery holder because I have a D batteries. If you happen to have a different kind of battery, you have to change your search, okay? Short of doing that, Play-Doh also, I have seen it where people use Play-Doh and it works. Okay? Does this help a little, Samantha? Or was it Samantha who asked or somebody else?
I was asking Alicia.
Alicia, yes, okay.
And then just one more thing. When we complete the motor, and I guess what is the day that we submit the actual video?
It's gonna be on Thursday after we come back. I'm gonna send you again, hopefully no later than the end of tomorrow. I'm working on a place where you guys are going to upload your videos. So once you're done, you upload it there, and we're going to share it on the day of the Thursday after the Thanksgiving. I don't know what that is. This is the 2nd or the 3rd of. Is it the 3rd of December or something like that? December 3rd. Okay. Because December 10th is going to be our final. So for those of you who are doing the motor, that would be the last day that I'm going to see you. Those who are not doing the motor, I still have another day when we meet. Okay?
When will we be getting our the instructions for the motor?
For building the motor?
Yeah.
There is no more instructions. Basically, I showed you, I demoed you how to do it, and you're going to do it. Oh, in terms of what to do, yeah, I think I also shared with you that you're going to show me that you did it during the process. So you need to take some pictures during that time, showing your face while you're working on it, or video. Okay, you don't have to give me from the beginning to the end, at least some.
Oh, okay. Oh, I think he went dark again. Yeah.
Okay, so if I'm understanding, we're not doing the actual demo on the 3rd, correct? He's just uploading the video. Is that what I'm understanding?
No, I think on the Thursday after we come back from break, we're gonna have to like upload a video of us physically, like I don't know if I don't think putting it together, but at least demoing it,
That it works,
activating it. Yeah,
right?
that's what I'm thinking.
Okay.
Yeah,
Okay.
It's
Okay. I thought it
because
was
I
gonna
don't
be
think.
like a live thing, like he's gonna call on us and then we would show it.
I mean, if it is, then okay.
the the lab says you need to upload your own video and making the motor, including your face
Oh,
and making it, or including your face while making it.
Yeah,
The
that's what I read
request
too. I
is
saw
that
that.
from Lab 10? Because yeah, right.
11 or
Oh,
whatever day.
10. It should be 10.
10?
yeah.
Yeah, it should be
Okay.
10.
I just
Okay.
checked the box and I didn't read anything.
Oh my
Okay, makes more sense. That's why I've been in the dark this whole time. And then, yeah, Jose,
I
that was a good question you made, man.
Video requirement. Because
I would
it
just
says
make
right
sure to
here.
buy the material ASAP.
I just copped a battery holder right now. I said,
Yeah,
nope,
I
I gotta
already
get
bought
that.
it too. I just bought
Yeah,
that.
I just opened up Amazon. I was like, I'm gonna get, and then Amazon's got the 4-pack, I guess, for like $6.50.
Yeah.
Yeah, I'm gonna get that right now too.
I have no idea what's going on. I heard some of you guys talking about what's going to happen on Thursday. I can hear everything, but I cannot read it. I'm closing it up. And I'm jumping up and down here, screaming at
I
my
think your
screen.
computer is ready for Thanksgiving break, Professor.
Yeah,
Listen, okay, the ideal thing, honestly, is for me, guys, to fix the link for you guys to upload your videos. That way you can basically be ready to do it. If we're in class, actually, I would ask you to go in front of the class and demo yourself, okay? Since we're not in the class, that's probably the thing that I want you guys to do, okay? And I'm hoping that you guys will allow me to share it with other faculty to basically show how proud I am of what you guys are doing. So that's one thing. And now, if that doesn't work, we still can do YouTube thing where you guys can upload it and you can grab it from there.
I was gonna say
But the thing
YouTube.
with it is I want to see that you guys are showing the motor, that it's working and how you built it. Now, again, you could do a summary, hopefully no more than 15 minutes. This is what I did, this is what I did, and you show exactly how you're putting it together, and this is what I did. And the principle for it is that as this one is turning because it has a torque due to the fact that it has a magnetic field and a magnet is trying to align with the current. And this is keeps in motion, and that's basically how it's working. So you could explain it that way,
We could,
and you
like,
have,
oh.
yeah.
Oh no,
Okay.
like we could like do a voiceover of it basically.
Yeah, you could, but at the end, you could record it with your cell phone if you want to. Okay, cell phone will work fine. Okay.
What do we So is there a minimum time requirement? Like, can we do it like in 5 minutes, or is it?
I'm hoping that to have at least 10 minutes to 15 minutes, basically, where you can talk about it a little bit. Okay.
Okay.
I will see if I think it has to be around 10 minutes, basically, because you want to talk about the fact that you have a battery, you have conductors that double as conducting currents and also holding your actual rotors in here that are rotating, and how you build this one and how many turns you were able to do it. I mean, for me, I think like I have like, what is it, 11 turns or 7 turns, or I forgot how many I did. It's a long time ago. But for you need to keep track of this, and the fact that the more you have, the stronger the motor is going to be, and the fact that you brought a magnet and try to talk about your magnet. Is it a strong magnet? Is it a weak magnet? What do you think about it? How can you improve on it to make a stronger motor? And the fact that you have a 1.5 volt battery if you're using a D cell battery or a C cell battery, or if you decided to go with a 9 volt battery, which is those square ones, that's fine too. You talk about the fact that you have that, and the fact that what difficulty you ran into, for example, the battery holder, which is a big issue. For example, if you ran into and you couldn't find it, and you were trying to get it to work, and maybe you could tell the word that I swear it worked, okay, when I did it myself, but now it's not working, okay, because that happens too, and you run through the difficulty that people have to run through, and how can you make it true so that it works next time around. If it works, then you're happy it works, but then it falls, and so you're going to again talk about this thing. So that's a decent 10 minutes, okay?
Okay. And then the actual lab does say that you're going to provide us with recording steps and then a rubric. is that just going to be the recording steps? It would just be basically.
Yes, yes, the stuff I talked about. I'm going to send you that's I'm going to upload it for the rubric on how it's going to be graded. Once you
Okay.
do that, you get your grade and you're done with the class. And I hope you wish you success in whatever you want to do. Okay.
Okay.
Okay. I'm sorry for this. It's happened so much today. I have no idea. I think, like you said, my computer knows that something is up. Okay. See you
It's ready to
guys.
take a break.
Okay. See you
All right.
guys.
Have a good one.
You
Bye-bye.
too. Bye.
Thank you. Enjoy your break.
Bye,
You
everyone.
too.
Bye.